Hello, one and all, Jake here. And today we're going to go over a very interesting problem that I had once for homework in a probability class. Now, the problem is not actually a probability problem, it is a combinatorics problem, but if you didn't know, in most probability classes, at least in college, the first unit is usually all about combinatorics because, well, you can't really solve a probability problem that's sufficiently tricky unless you really understand the sample space. And combinatorics can let you understand that pretty easily. So this is just some stuff I was working on earlier. I'm going to erase this. I'll be back in just 1 second through the magic of editing. And voila, this right here is the problem. Now, if you can't read my chicken scratch handwriting, I'm just gonna read it to you. It says, there are 8 people on an elevator that stops at 6 floors. Some number of people get off at each floor, and all are dropped off by the stop at the 6th floor. In how many different ways could the people have been dropped off, treating each person the same? In other words, you have an elevator that's stopping at 6 floors, and you have to count the number of ways in which you can drop off 8 people at these 6 floors. So you can go ahead and give this problem a try yourself. I'll let you pause right now and do that. Okay, welcome back, and I will let you know right now that if your answer was, well, there are 8 people and there are 6 possible floors that each one could have gotten off at, so we have 6 possible floors for the first person to get dropped off at, times 6 possible floors for the second person to get dropped off at, and so on, all the way up to the 8th person. Well, then it's just 6 to the 8th power different ways to drop them off, right? If this was your answer, I'm sorry, you misunderstood the problem. The key line here is treating each person the same. So if I have person A going to floor 1, let's just say A going at floor 1, and then I have person B getting off at floor 2. This is one way you could drop off person A and person B. Now, if I switched the two, well, this method of counting them would count this as a different way you dropped off the people, but the point is you dropped off one person at each floor, and so this is actually not a different way to drop them off. So treating each person the same is a key detail, and I think you'll notice that this makes the problem a lot harder. So how on earth would you go about solving this problem? Well, one thing you might consider trying is just systematically listing out all of the different ways to drop off the 8 people on the 6 floors. And to aid with this, I'm actually going to draw a picture, and we're going to keep this on the board for a little while, as a matter of fact. So here's floor 1, here's floor 2, 3, 4, 5, and 6. By the way, this is America. Our ground floor is floor 1, all right? So British people, don't flip out at me. This is just how we do it here in the States. Anyhow, let's just say we drop off 1 person here and then 2 people here. Each of these circles is going to represent a person. And then no people at floor 3. And then 3 here. And how many do we have so far? We have 6. So 1 at each of the remaining 2 floors, and that's 8 people, right? And then let's just say instead of dropping 3 people off at floor 4, we drop 1 person off at floor 3 and 2 at floor 4. That's another way that you could drop off the 8 people. And, maybe there is some sort of systematic way to make sure you don't double count anything and it all makes sense. But if you do this, you'll find that it's going to take a really, really, really long time. Like, absurdly long. So is there a better way? Can we do something that's easier? One thing you might consider trying is setting up some sort of multiplication, similar to what we did earlier, but keeping in mind the fact that we're supposed to treat each person the same. However, you quickly run into the realization that this won't work. So let's just erase all these people for now. we could drop off 8 different numbers of people at the first floor, right? Now, how many different numbers of people can we drop off at the second floor? Well, it actually depends on what you choose for the number of people you could drop off at the first floor. If you drop off all 8 people at the first floor, then there's only one possibility for the rest of them. And if you drop off 7 people, well, there are 2 possibilities. You can either drop off 1 or 0 at 2. So this sort of method, I mean, you're going to end up expanding out all the possibilities into a tree that's just as tedious to parse through as just drawing it out and listing them. So similarly to the previous method, this gets too unwieldy too fast. So what are we to do? Because it seems like all of the obvious approaches to solving this problem are crashing and burning very quickly. Well, whenever I'm in a position like that, I like to try to rethink the way I'm considering the problem. So let's just take any random way to distribute the people amongst the 6 floors. Let's see. Yep, that's 3, 6, 8. Yep, that's 8 people. Now, what we did here was we drew circles representing all the people, and we drew them next to the floors. But what if we flip that on its head a little? What if we have the people already, and we draw the floors in? Maybe that might lead to a way of thinking about the problem that's closer to something solvable. So what we're going to do is we're going to draw 8 circles representing the 8 people. We're going to leave some space in between them for a reason I will disclose in a second. Now what we want to do is we want to take this method of drawing out the way to distribute the people, and we want to convert it into something that we could do here horizontally. And what we're going to do, notice how we drop off 2 people at floor 1. We're going to draw just like a little dividing line after 2 people here. Now we dropped off 0 people at floor 2. So we're going to draw a dividing line here. Now there are 3 people being dropped off at floor 3, so we skip the 3 in between spaces and draw the line here. And 0 at floor 4, 2 at floor 5, and 1 at floor 6. Now notice, there are 5 dividing lines here, and there are 5 dividing lines between the floors here. So basically, like, we're splitting up the people with these lines based on where we're dropping them off. So we have the 2 at floor 1, 0 at floor 2, 3 at floor 3, 0 at floor 4, 2 at floor 5, and 1 at floor 6. So now I'm going to erase these lines and draw 5 more in just arbitrary spots. All right, so I'm going to put 1 here. Actually going to put 1 here. 3, 4, 5. And what we're going to do now is we're going to erase what we had previously. And we're going to convert this into this format, just so it's clear like exactly what's going on. So we have a dividing line right away, which represents 0 people being dropped off at floor 1. Here we have floor 2, there is 1 person being dropped off. Floor 3, we have 2. Floor 4, we have 1. 5, we don't have anyone. And 6, we have a whopping 4 people. I guess everyone wanted to get off at floor 6. Maybe they had free bagels at an office party on that floor. I don't know. But so we can see that for any 5 locations to place the dividing lines, we can convert it into an equivalent way to distribute the 8 people. So what we did was we've changed the problem from how do I distribute 8 people onto 6 floors into how do I distribute 5 lines into, 9 different slots. The gaps on either side of the people are slots, and there are 9 of them. But the problem with this is that well, we kind of just kicked the problem somewhere else, didn't we? The number of ways to distribute the 5 dividing lines amongst the 9 slots will be the same as the number of ways to distribute the 6 people among the, the 8 people among the 6 floors, but we still run into the same issues when we try to count the number of ways to place the dividing lines. It's no different. So unfortunately, this won't work either. But let's not throw out this idea entirely. Now, what would be really convenient, and let me just erase these dividing lines, is if we could guarantee that at least one person got off at each floor, right? So if at least one person gets off at each floor, how many different ways are there to drop off the people? Now, this actually becomes possible because let's just draw these 7 blanks in between the 8 people. It's guaranteed that only one dividing line will ever occupy a slot here. You can't have 2 because at least one person is guaranteed to be dropped off at each floor. So, for instance, let's take 2, 3, 4, 5. This would correspond to this distribution of people. Now, as you can see, there aren't actually many ways to drop off the additional people because 6 of them are, forced to sort of be dropped off at a particular floor. So the number of ways there are to drop off all these people, given that at least one gets dropped off at each floor, well, we can sort of measure that using what we went over last video. And I'm going to leave the link to that in the corner. I think it would be in this direction of the screen. I'm not positive though. But yeah. Notice how we have 7 different slots and we have 5 dividing lines. So how many ways are there to choose 5 slots where the dividing lines go out of a pool of 7? Well, there are 7, choose 5. And if you recall from that video, that would be 7 factorial over 5 factorial times 7 minus 5 factorial. And that is not a very big number, which is appropriate because, the number of ways you could sort of drop off these extras also isn't a very large number. So this lends some credence to the idea that this method is the right approach. But there's a problem. We actually can have 0 people being dropped off at each floor. So what are we to do now? What if we made it so that there actually has to be a person being dropped off at each floor, but not really? Here's what I mean. Let's say we have just 6 ghost people that are always going to be dropped off at a floor. Now, the elevator goes and drops off a ghost person at 1 per floor, in addition to the 8 real people that are already in the elevator. So an example might be 1, 2, 3, 4, 5, 6, 7, 8. I'll lay out like this. Now, in what I'm about to draw, I am not going to draw the ghost people for a reason that should become clear very soon. So there are 14 total people, 8 normal people and 6 ghosts. All right, now we're going to draw the blanks. Now I'm doing this across 2 lines because I kind of ran out of room, so we're just going to draw the blank between these 2 here. I hope you are okay with that. Now, how do we draw this arrangement of dropping people off using our dividing lines as we did before? Well, 3 are being dropped off at floor 1, and we have 3 at floor 2. Then we have 1 at floor 3. We have 4 at floor 4, 1 at 5, and 2 at 6. And, we don't draw the last slash, but there are indeed 2 people left. That is an indication that we're doing this in a way that makes sense. Yeah, as you can tell, this distribution corresponds to this distribution of these slashes in these slots. And here's the important part. Every single distribution of these slashes amongst these slots corresponds to a way to drop off the 6 ghosts and the 8 real people amongst the 6 floors. And they have a one-to-one correspondence with the way you can drop off just the 8 people, because it's guaranteed that exactly 1 ghost person will be dropped off at each floor. The total number will actually be the same. So if we just look at this alone, it looks like what it represents is 3 plus 1 plus 4 plus 1 plus 2 equals 14. But what it actually represents is 2 plus 2 plus 0 plus 3 plus 0 plus 1 equals 8. And if you're willing to add the numbers up, you'll see that indeed this holds. So, does this bring us any closer to an answer? Yes, it does, because now we have 13 different slots to distribute 5 dividing lines into. How many ways are there to do that? Well, there are naturally 13 choose 5 ways to do that. And this is actually our answer. That's right. There are 13 choose 5 ways to drop off 6 ghosts and 8 normal people amongst 6 floors. And therefore, there are the same number, 13 choose 5 ways to drop off 8 people amongst 6 floors. Hello, one and all, and welcome to a brand new segment of the show known as Jake at his computer, where I do some computer stuff, I guess. Now, here we have Wolfram Alpha, which is a very useful website where you can just type in whatever you want and it'll calculate it for you. Provided that it's mostly mathematical in nature. So for example, let's take our answer that we got, which was 13 choose 5. And give it a sec, and bam, here we go. 1,287 is the result. Now, this number, might not seem like as much as you might have thought, but it's still pretty large, and it probably would have taken a long time to systematically, see all the different ways that you could drop off the people across the 6 floors. I'm going to minimize this window, and bam, what have we here? Well, see, there's a device that makes systematic, repetitive calculations very, very simple by design. It's called a computer. So here we have part of a C program I wrote that actually will loop through all of the possible different numbers of people to drop off at each of the 6 floors. Now, if you're not familiar with what a for loop is, I'm going to try to explain it in a very brief way. Here we have this integer that we call ways, and I set it equal to 0 first. And in this internal loop, which F6 indicates that it keeps track of the 6th floor, number of people being dropped off, it will increment from 0 to 8, and then it'll say, if we add up all the different numbers of people that we dropped off at this floor, does it equal 8 total people? If so, then this counts as a way to drop off the 8 people across the 6 floors. If not, just keep incrementing. Now, once this f6 variable increments from 0 to 8, it's going to increment f5 to 1, and then it'll check, 0 through 8 again. And obviously, 1 plus 7 will equal 8, so then that will count as a way. And it'll continue outward that way until you've checked all of the possible different numbers to distribute across the 6 floors. And it should print out the number of ways in total there are to distribute the 8 people among the 6 floors. Now, if I recall from Wolfram Alpha, that answer was 1,287, and that is the answer we got on the whiteboard using our method. So let's run this program and just see what number it spits out. Oh, hey, look at that. Number of ways found, 1,287. It's the same. Look at that. So if you were skeptical at all about the answer we just got, then hopefully this alleviates those concerns. This is indeed the correct answer. All right, welcome back. And now we have a part B of the problem. And indeed, there will also be a part C, so don't touch that remote. But what about dropping off 5 men and 3 women, treating the members of each sex the same? In other words, we have 5 men that we're dropping off, and we have 3 women that we're dropping off. Now I want to use the blue marker to represent men. If we have, man A and man B versus man B and man C being dropped off at floor 1, well, that's fine. That's the same. The point is the number of men. But if we have, 1 man and 1 woman, now that's different because, it's a man and a woman instead of 2 men. So again, treating the members of each sex the same, but not treating each sex the same. How many different ways are there to drop off the 5 men and the 3 women? Now, this might seem a bit harder, but we can sort of use what we've already learned. And let me just erase this and demonstrate what I mean. So if we distribute the men as follows, let's just say there's 1 on 4, 1, 2 on 4, 3, 1 on 5, and 1 on 6. And then the women, we again have 1 on 4, 1, 1 on 2, and then 1 on 5, for instance. All right, this is just an example. Here we have a distribution of men and a distribution of women in the same sort of way, we're going to call them. So let's just say we fix the way that we've distributed just the men, and we move a woman. Let's just say instead of being dropped off at 2, she gets dropped off at 4. Well, now this is a different way to drop off 5 men and 3 women, but only the women really changed. And if we were to count up like all the different ways to distribute just the 3 women among the 6 floors, then, we take that number, that applies to this distribution of the 5 men here. Now, if instead we distribute the men this way, well, then notice we can still have the exact same number of different distributions of women. It's just that now the men are distributed differently. So we have the number of ways to distribute the women. We actually multiply it by the number of ways to distribute the men, because for each of the ways to distribute the men, you can apply all of the different ways to distribute the women, and they all count as different. So this sort of approach, you have one action, you have another action, and they're independent from each other. So the compound action is the product of the number of ways you can perform both. That's called the fundamental counting principle. And while that kind of sounds like a crazy joke, it's actually a very important principle in combinatorics. So we have the action of dropping off the 5 men across the 6 floors and the action of dropping off the 3 women across the 6 floors. So the compound action of dropping off the men and women across the 6 floors is just going to be the product of the number of ways to do each of the constituent actions. So if that makes sense, then we can proceed with the rest of the problem. So let's just take this guy off 3, put him back in 2, and how many ways are there actually to distribute just the men? Well, what we're going to do is we're going to do the same thing. We're going to introduce the concept of ghost men. Ooh, so we have 5 circles representing just the men. Then we're going to add 1, 2, 3, 4, 5, 6 circles that represent the ghost. Remember, there's still 1 ghost for each floor. That hasn't changed. And now we're going to add the slots. How many slots are there for the dividers? Well, each of the in-betweens has a slot, and there are 11 circles, so there are 10 slots. And once again, there's 6 floors, so if we're trying to sort of divide these circles out, you'll see that there should be 5 dividers. So in other words, we have 10 slots for the dividers, and we're going to choose 5 of the slots to actually insert the dividers into. So the number of ways to distribute just the men is 10 choose 5. And I'll leave as an exercise to you, the viewer, how many different ways are there to distribute just the women. And you can use the same exact approach. If you do it correctly, you'll find that there are 8 choose 5 ways to drop off the women. And yeah, this is your answer. 10 choose 5 times 8 choose 5. Now again, I don't know what number that is exactly off the top of my head, but it doesn't really matter for our purposes. This is the answer. Hello again, and welcome back to Jake at his computer. Here we have the calculation from last time, and what I'm going to do now is I'm going to actually calculate the actual number we just got. So there was 10 choose 5 times 8 choose 5. And here we have 14,112. This is a much bigger number than 1,287. And that should sort of align with your intuition that there are probably more ways to do it if you consider separate cases separately than if you consider every single person the same. So we have men and women this time instead of just people. So it makes sense that there are a lot more ways to do this. But this number, well, can we confirm it? Here we have the same C program I had before, but if I scroll up in the source code, and this is the reason I didn't show the whole thing, we can see there's another mode that this program has, another option, if you will. It's a sexism mode. If you type the S flag when you run the program, it'll solve the problem for 5 men and 3 women instead of 8 people. And it does a similar thing, except it, stores the number of men being distributed from floors 1 through 6 and the number of women being distributed from 1 through 6. And then it checks to make sure that the total number of men dropped off is 5 and the total number of women dropped off is 3. If that is the case, then it adds 1 to the number of ways, which is initially set to 0. Now, I know you comp sci people are going to flip out at me like, oh my god, this has n to the 12 runtime. Oh my god, this can't be any less efficient. Relax, all right? Calm the hell down. It's just, our n doesn't even get that big. Like, it's not a big deal. And yeah, it's just gonna print out the number of ways there are to distribute the men and the women among the 6 floors. And so let's just do that. Let's just add this S flag. And we can see indeed that our answers agree, 14,112. Now, I'm going to run it again, and I want you to take note of the slight delay between it finding the number of ways and it printing. Compare the original mode, which had very little delay. Now, I know I just made fun of the comp sci people for what they said about the runtime, but it is indeed a lot more cases it's checking. And so that is why there is a bit more of a delay. But yes, our answers agree is the end result here. And hopefully that takes away any skepticism you might have had about the answer we just got in part B of the question. I'm going to take it back to the whiteboard now. Hi, welcome back to Whiteboard Jake. Now, part C is, what about if we drop off M men? No, I don't have a stutter. I just used the letter M to represent the number of men. M men and W women across the R floors. And let me just add a freaking ampersand because I forgot to, make it a compound subject. Anyway, basically what we have to do here is we have to generalize what we've been doing the entire time. And if you have a full grasp of exactly, why the method works and what exactly is going on, then this shouldn't be too hard, but I'm going to walk you guys through it. Now, take note of the fact that we can just treat the men and women separately just as we did before, and then multiply the results together. So we're going to deal with the men first, just because I have them written down first. How many ways are there to drop off M men across R floors? Well, to find that out, we're actually going to use the ghost method again, but we don't have actual numbers, so we're going to have to sort of improvise what would be there. So if we have M men and R floors, how many men and ghost men would we have written down as circles? Well, we have M men, R floors, one ghost for each of the R floors. Sounds like M plus R. So yeah, we're going to write down M plus R. We're just going to keep that there just for now. Now an important thing we need to ask is, how many slots would there be with M plus R circles written out? Well, each of the in-betweens has its own slot, so there would be M plus R minus 1 total slots, right? Now the last bit of information we need is how many dividers are there going to be. And when there were 6 floors, there were 5 dividers. And conceptually, that sort of makes sense. If you want to divide a cake into 6 pieces, cutting along one way, you would make 5 cuts. So if you want to divide a cake R ways, using cuts along the same way, you would use R minus 1 cuts. So yeah, this is our answer for the number of ways to distribute just the men. And the women would follow much the same pattern. It would be W plus R minus 1, choose R minus 1. And of course, the last step is to multiply these two together. That should be rather obvious. And yeah, so this is our generalized answer for any number of men and any number of women and any number of floors. We could solve the problem we just solved. Now, let's just do a little sanity check on this. First of all, if there are 5 men and 3 women and 6 floors, just as we had before, this would be 5 plus 6 minus 1, so that's 10, and then 6 minus 1, that's 5, that's 10 choose 5, and here we would have 3 plus 6 minus 1, that's 8, and then 6 minus 1, that's 5. So we have 10 choose 5 times 8 choose 5. That is exactly the answer we got in part B. Another sanity check we could do is, what if there are 0 men and 0 women? Well, then we're left with 0 plus R minus 1, choose R minus 1. That's just R minus 1, choose R minus 1. and any number choose itself is just 1. And similar here, when there's 0 women, it's just going to be r minus 1, choose r minus 1, or 1. So we have 1 times 1, which is 1. And indeed, if you have 0 men and 0 women in the elevator, there's only one way to drop them off across the r floors. Namely, it's to not drop off any of them at any of the floors. So that actually makes sense. Now, one last thing we could do is, let's just say there are 8 men, 6 floors, and 0 women. What are we left with then? Well, let's plug it in. For the women, we know that it's going to be 0 plus r minus 1, choose r minus 1. That's just 1. Now for the men, we have 8 of them and 6 floors. So that's 8 plus 6 minus 1, which is 13. And then 6 minus 1 is 5, so that's 5. 13, choose 5 times 1. And if you remember, that is exactly the answer we got for part A. And, if you're to have 0 men and 8 women, it would also be 13, choose 5. So, yeah, this problem is not sexist in any way. It doesn't really matter which number you assign to men and which number you assign to women. They're in parallel. But the idea here is that if you have only one category of person in the elevator, so in here we only have men in the elevator being distributed, then, in part A, the way we got this answer was by having only one category person, namely person in the elevator. We're treating them all the same. So, yeah, if you have 0 of one category and, 8 of another and then 6 floors, that reduces to the same problem we solved in A. And this is also a good sanity check to make sure that this checks out. This makes sense. And I hope you are thoroughly convinced that this generalized answer holds. Just to make it a bit more rigorous, we're going to impose some restrictions, by the way. So it's important that R is a member of the natural numbers, because if you have, for example, -3 floors, well, then the whole problem kind of breaks. So that doesn't really make any sense. In addition, M and W have to be in the natural numbers, or they can also be 0. And that would also work. Alright, I didn't notice this while I was recording, but can we please get an angle check on this board? I mean, this has got to be at least 30 degrees from the plane of the ground, right? That's a crazy angle. I'm so sorry, guys. I didn't realize I was drawing this diagonal. I'll try to fix this in the next video, but wow, I mean, that's ridiculous of an angle. So yeah, that's the problem. I hope you found it as interesting as I found it when I first encountered it. What I like so much about it is you have a problem that is pretty simple on the surface, and you add more elements to it to make it possible. In geometry, you'll often have geometric proofs that require you to draw auxiliary lines and make, perpendicular bisectors and stuff like that on the figure that weren't there to begin with, that actually make the problem possible. And here you have the same sort of deal. You didn't start off with this entire concept of a ghost person in the elevator, but by introducing it and sort of adding a complication to the problem, it actually makes it easier to count the ways to drop them off. So that's what I found most interesting about it. I hope you agree with that. If you have any feedback, please leave it in the comments. Feedback is very important, because I don't want to be making a consistent mistake that makes these videos less watchable than they could be. I want you guys to let me know if there's anything I can improve. I also have a couple more math related videos planned, quite a few actually. So I'm going to be continuing to upload math related, combinatorics and probability and stats related mostly on this channel. And I want you to stay tuned for that. But yeah, that's pretty much it. I have nothing else to show you guys for tonight. Please remember to stay awesome, and to hug your mom, and to hug yourself if you don't have a mom. That got kind of depressing. Now, I want you to go and find out which of these circles is the worst. Because personally, I think it's this one. This is probably the worst circle I've ever drawn in my life. Actually, let me redo that. And okay, that was a little better.